Hello everyone, welcome. In this video, we will discuss a procedure for solving the Gaussian integral, which is the definite integral from negative infinity to infinity of e to the negative x squared dx. This integral shows up in many key places in physics and engineering, and its result is rather elegant. Before we begin, we should note that there are several ways to evaluate this integral. The method presented here is a somewhat simpler method involving multivariable calculus. Let us first analyze the plot of the function we are trying to integrate. We can plot e to the negative x squared on the zx plane, and remember the value of the integral is simply the area under the curve, which we will denote as I. If you were to approach this integral using the standard first-year calculus toolbox of integration techniques, you will pretty quickly see that there is no immediate antiderivative, substitution, or integration by parts we can readily apply to get us closer to a solution for I. So instead, we will carry out the seemingly arbitrary action of rotating the coordinate system by 90 degrees, and then once again plotting the same exact function, but this time on the zy plane instead. The same function on the zy plane is, this time, e to the negative y squared. And as far as the area from negative infinity to infinity, since the function is geometrically the same, all we did was switch x with y, this means the area would simply be the same as the original integral I. Now it may seem like we haven't progressed in solving our original integral at all. In fact, it seems like we've actually just restated the original problem. And while all of this is true for the time being, it turns out we can take advantage of some very convenient geometric properties of these two perpendicular areas when we multiply both of these areas with one another. After multiplying these two integrals with one another and simplifying, we end up with the following. This now double integral essentially represents the volume that is produced by multiplying the shapes of the two red and blue perpendicular areas. We see from the 3D plot that our original area was effectively just revolved about the origin, producing the volume I squared. Now you might be wondering, how are we any closer to solving the original integral? In fact, it seems like the problem just got more complex since now we have two variables that we need to integrate with respect to, neither of which can be availed to any obvious substitution or integration by parts. At present, all of these observations are true. However, the key to turning this integral into something manageable stems from the now axis-symmetric nature of the 3D surface. Let us examine a circle on the surface centered at the origin. We see that we have our xy coordinates, as usual, which vary as expected as we move along the circle. However, we can avail ourselves to a different way of looking at the circle. We can instead define any location on the circle in terms of the radius r and the angle made from the x-axis theta. The circle can just as easily be described in these coordinates, which are known as polar coordinates. Not only this, but we can use some simple trigonometry to cast x and y in terms of r and theta, where x is r cosine theta and y is r sine theta. Nothing has really changed here. We are still describing a circle, but instead of describing it in terms of the Cartesian coordinates x and y, we are using the polar coordinates r and theta. Going back to our integral, let us write x and y in our double integral in terms of r and theta. After plugging the polar coordinates of x and y and applying laws of exponents and pulling out the r squared, we end up with the following. Let us not forget that cosine squared theta plus sine squared theta is a well-known trigonometric identity, which is just 1. We now end up with the following integrand in terms of r, and technically theta too, even though there is no theta parameter present. Now that we've written the integrand in terms of the polar coordinates r and theta, we need to integrate with respect to r and theta, not with respect to y and x. So the differential Cartesian area element dy dx must be replaced with a differential polar element in terms of dr and d theta. So how can this be done? There are a couple different ways this can be accomplished. In this explanation, we will take a geometric approach, since it's one of the more intuitive methods. We could also use elements of vector calculus and something called the Jacobian to accomplish this, but we will hold off and stick with the geometric approach for now. We first need to understand what a differential element looks like in each coordinate system. In Cartesian coordinates, this is very simple. We simply have a rectangle with length dx and width dy. We can simply multiply these, which results in the area of the differential element dy times dx. The polar differential element is quite different. It's essentially a sector of a circular ring with thickness dr. The arc length of the inner ring comes from the relation for arc length, which is the radius times the change in angle. In this case, since the element is differentially small, the inner arc would just be r times d theta. We can apply the same intuition for the outer arc, resulting in the outer arc length of r plus dr times d theta. The extra dr is due to the differential thickness of the element. We can now represent the area of this differential polar element by simply writing out the area of the ring sector. We can first write the total area of the circle that lies on the outer arc, pi times r plus dr squared, and then subtract it from the total area of the circle that lies on the inner arc, pi r squared, giving us the area of the ring on which the differential element is enclosed. We can then multiply the ring area by the fraction d theta over 2 pi, giving us the area of the ring sector representing the polar differential element. This undoubtedly looks more complicated than the Cartesian element dy dx, however, there is a compactness that becomes more apparent when we multiply everything out and simplify. After doing so, we end up with the following. This still looks a bit complicated and perhaps somewhat difficult to interpret, but the key is to take advantage of the reality of what it means to produce a differentially small quantity. Let us take dr for example. What does this mean? This means we take some finite difference in r values and push that difference to be as small as possible without ever getting to zero. So what does this mean for dr squared? Well, applying this principle to dr squared just means this quantity would have comparatively long gone to zero way before dr would have, which means it's effectively zero in the presence of any dr term, even though it too can technically never be zero. This means we could simply erase the term due to its tendency to comparatively vanish in the presence of the first term. After applying this and simplifying and rearranging, we end up with the following representation of a polar differential area element, r dr d theta. We've now successfully produced a polar differential element that we will be integrating along with the polar variables r and theta. We could start by replacing the inner integral's differential dy with r dr. Doing this is not as simple as just replacing dy with r dr. We also have to replace the integration bounds, which were originally in terms of y. Y went from negative infinity to infinity, with the integration bounds in terms of r now. This is somewhat obvious when we examine the plot of the 3D surface. We ask ourselves, in order to construct the surface, where does r start and where does it end? Well, it simply starts at the origin where r is 0, and it extends out to infinity in all directions. So the integration bounds for the integral involving dr is simply 0 to infinity. Next, we can replace the dx in the outer integral with d theta, and again we have to replace the x integration bounds with bounds in terms of the variable theta. This can again be done rather easily by observing the 3D plot. We see that in order to construct the surface, theta must start at 0 and go all the way around, ending at 2 pi, which means the outer integral bounds must be from 0 to 2 pi. We now have the same double integral, except now it's completely defined in terms of the polar coordinates r and theta. So what was the point of all this? Well, this integral has a vital artifact that didn't exist in the original integral, and that is the extra r factor that precipitated from the arc length relation. This r factor allows us to make the following substitution. We can call r squared u, which means du dr is simply 2r, which means dr is simply du over 2r. After plugging in the definition of u and the relation for dr, we can cancel out the r's and pull out the 1/2, resulting in the following transformed integral. At this point, we have to address an important, but in this case slightly pedantic aspect about this integral. These bounds are technically not applicable to the inner integral, since these integration bounds are applied to the variable r, but we transformed r to u, so we need to determine what these bounds would be in terms of u in order to apply them to the inner integral. We can do this easily by just determining the values of u at the r values infinity and 0. Since we've already defined the relationship between u and r, we can plug infinity in for r, which results in u also being infinity when r is infinity. We could do this again for 0, and we end up with u also being 0 when r is 0. Which means the integration bounds in terms of u instead of r are also 0 to infinity. This may have seemed unnecessary to do, but the fact that we ended up with the same integration bounds for u that were already present for r is entirely coincidental, which is why time and care should always be taken to change the bounds in terms of the variable we are integrating with respect to. At this point, we should be able to evaluate the double integral using our basic knowledge of antiderivatives. Starting with the inner integral, the integral of e to the negative u is simply negative e to the negative u, which we can evaluate on the interval from 0 to infinity by subtracting the lower bound from the upper bound. After evaluating and making simplifications, we simply end up with the inner definite integral being equal to 1. We can do the same with the outer integral, which is just theta, and evaluate it from 0 to 2 pi, ending up with 2 pi. After simplifying, we obtain the following result: I squared is pi. But let's not forget the original objective was not to find the volume I squared under the 3D surface, rather it was the area I under the 2D curve. Which means we simply need to take the square root of both sides, ending up with I is equal to the square root of pi, which is the final result obtained from evaluating the Gaussian integral.